Hello everybody. Today we're going to finish up the projectile motion notes by looking at non-symmetrical parabolas. Now this is talking about objects that vertically do not end at the same place as they begin, like they did with the full symmetrical parabolas. But they still have both the up and the down motion. So for example, you could have something that starts above where it ends up, okay, and it's going this way. All right, you could also have something that starts below where it ends up, right here, okay. Now in this case, the vertical displacement is no longer zero the way it is for a full symmetrical parabola. So let's take a look. First, because we are going two different directions in the vertical plane, then we need to make sure everybody's on the same page with directional signs. We're going to let up be positive direction and down be the negative direction. So any vectors that we use must have those appropriate signs. An object that starts above where it ends up starts with an initial y position right here and ends up down here. So your vertical displacement or your vertical change in velocity is downward. So it's going to be negative. All right. On the other hand, if you end above where you start, then you will start with an initial position down here and end with a final position up here, so you end up going this way when you displace vertically, and we'll consider that a positive vertical displacement, okay? So if you go down from where you start, that's a negative displacement because down is negative. If you go up from where you started, then that'll be a positive displacement, okay? We're not going to go really through the horizontal motion because like the half parabolas and the full symmetrical parabolas, the horizontal motion is just as it's always been. Constant velocity, no acceleration. So mainly what we're going to be looking at are the differences, which again lie in the vertical plane, okay? So first off, we still have a vertical initial velocity, and that would be in both cases. You still have an initial vertical velocity that is a component of the overall initial velocity, all right? So for these two, that component would be here and here. And again, it would be v sub y equals v sub sine theta in both cases, where this is angle theta. Whoops, not terribly good right there, but oh well. All right. That velocity decreases until it is zero at the top. So the y velocity at the top is still zero in both cases. However, one thing you should note, we've lost symmetry. So does it take half the total time to get to the top? Think about it. You're going to subtract fewer 9.8s to get to the top here, and you're going to be adding back more 9.8s than you took away here. So it's going to take more time to come back down here, less time to go up. So it's not half the total time. In either case, it's no longer half the total time. So in both cases, the time to the top is no longer half the total time, half the hang time. Now, what does that mean for us? Well, basically, it means that we no longer have two ways to find the maximum height reached by the ball or the object. We only have one, and that's using the alternate equation, starting with your initial vertical velocity and decelerating to a stop at the top. There's no other way, guys. That's it. That's what we have to do because the time to the top is no longer half the total time, so we can't use our symmetry there. All right, we know the vertical acceleration is still g, which is negative 9.8 meters per second squared. All right, and remember, they're never going to tell us that. We have to know that. Another interesting difference is that when the ball hits the ground, the final velocity no longer equals the initial velocity, again, because of our lack of symmetry. The vertical component here, the final vertical component in the y-plane, is going to be bigger than the initial vertical component. It has to be, because you accelerated down further than you decelerated up to a stop. So it's going to be bigger here than it is here. And just the reverse for this one. Here it doesn't come down as far, so it doesn't have as much time to accelerate to the same vertical velocity you had there. So here the vertical velocity is actually going to be less than it was here. Okay? Let's see. Another interesting piece of information we need to know. Well, actually, I think that's about it for this. So let's answer these questions. How is the vertical displacement different from a full symmetrical parabola? Well, first off, it's no longer zero. We've lost our symmetry, right? So the distance that we go up to the maximum height is no longer the same coming back down. We go from the ground up here, and then we come back down to the height of this surface. Over here, we start at the height of the surface and go up, and we come all the way back down to the ground. So those two do not cancel out like they did in the full symmetrical parabolas. So you're going to either have, it's either a positive displacement or a negative displacement. Okay? Now, next question. How much time does it take to get to the top? All right. Unknown at the moment. Because the time to the top does not equal half the total time anymore. Now, there are ways that we could find the time that it takes it to get to the top, like using the definition of acceleration. But sometimes it's easier to work your way around it. For example, if we need to find out how high the ball goes from here to here, we just use the alternate equation. The alternate equation takes you from your initial velocity, decelerating to a stop at the top. You'll get this measurement here. If you know what this one is already, you just add the two together to get the total height above the ground. Kind of cool. Now on this one, you can do the same thing, but you don't have to add anything because your initial vertical velocity already starts on the ground. You decelerate to a stop at the top, so you will get, from the alternate equation, the total height from the ground up. Here you would have to add a piece from here up, add that. But here, it's already included with the alternate equation, from initial to final. And we'll be looking at some examples of those, don't worry. Are the net initial velocity and net final velocity the same? No, because we lost symmetry. So they're no longer the same. Now the horizontal components will still be the same, but the vertical components will be very different. How would you modify the method of finding the maximum height reached by the projectile? we can only use the alternate, whoops, that was good, the alternate equation now, okay? We cannot use the general equation because we no longer know the time at the top. It's not half the total time. So we're down to one way. Now, let's see how we can use this information to solve a problem where we have a non-symmetrical parabola. Okay, so here's the fun. Look at this. A kid playing in his yard accidentally kicks a ball up into the air, and when it comes down, it lands on the roof of his house, which is 6.5 meters high. Like some of you have never done that before. The initial velocity of the ball is 6.8 meters per second at an angle of 55 degrees relative to the ground. If it takes 2.1 seconds for the ball to hit the roof, we want to find out how high the ball traveled above the roof and determine the final velocity of the ball when it struck the roof, when it hit the roof. Now, because it ends above where it started, we're going to be looking at this situation right here, aren't we? The ball is kicked. It was on the ground, now it's on the roof, okay? So the first thing we want to do, once we've read the problem and realized, oh, this is a non-symmetrical problem, we want to create our DVAT chart. So here we go, X and Y, split down the middle, a line here, split it in half, and split each half in half. Okay, and we're going to put D, V sub O, A, and T right there. Now, let's fill in some of our blanks, okay? It says that the ball goes up in the air and it comes down and lands on the roof, which is 6.5 meters high. So look, the ball is going to end up 6.5 meters above where it started. Above is positive. So for the vertical displacement, we're going to say positive 6.5 meters. Okay? It also says the initial velocity of the ball is 6.8 meters per second at an angle of 55 degrees. So our resultant initial velocity is 6.8 meters per second at 55 degrees. Now we can't use it in this form. So one of the first things we're going to have to do in a moment is take this and resolve it into the two initial components. Okay? Lastly, it says it takes 2.1 seconds for the ball to hit the roof. 2.1 seconds, 2.1 seconds. Okay? Now that's all the numerical information we're given. But there's some understood information that we can write in. We know the accelerations. The horizontal motion still being constant velocity, we can put a 0 in for the horizontal acceleration. That doesn't change. Also, we know the vertical acceleration is that due to gravity, and it always points down, so we can say 9.8 meters per second squared with a negative on the front. All right? Now, because they want us to find the final velocity of the ball, I'm going to add in one more box here. Okay, for the VF. In order to find the final resultant velocity, we need these two components so that we can use Pythagorean theorem and inverse tangent of the tangent ratio. So we can add those two components together. So we'll have a vertical final velocity component and we'll have a horizontal final velocity component, VFX. Okay, and we need those in order to get this. Well, now one of them is going to be pretty simple. Whatever this is on the horizontal side, it goes right here also because it doesn't change. Now, in order to get started, we need to take this initial velocity and resolve it. So, to get V sub O x, we're going to take the hypotenuse times the cosine of the angle, and that's going to be 6.8 meters per second times the cosine of 55 degrees. To get the y component, that's going to be V sub O sine theta. So that's going to be 6.8 meters per second, but we're going to take the sine of 55 degrees. Okay? Now, make sure, everybody check your calculator now. Make sure you're in degree mode. If you're in radians, you're going to get some weird answers. But if you're in degree mode, you should get 8.8 meters per second for the horizontal. So I'm going to put that here. And because it stays constant, it goes down here as well. All right. Now, the vertical, I got 12.5 meters per second for the vertical. So that goes over here, but it doesn't go down here because what we're going to see on the top, this is going to be smaller because it doesn't come down as far as it did going up. So this is going to be smaller than this one. All right. Now, let's take a look at part A. They wanted us to determine how high the ball traveled above the roof. Now, I want you to notice something. Here's the roof of the building. They want to know how far above that it went. They don't want this part. So they want from here up to the top. So what we can do is we can use the alternate equation to determine how far the ball went vertically from here to here. We can find all of this, then subtract out the height of the roof, okay? And that will leave behind this much, okay? That's what we're going to do right now. So let's try it, okay? Here we go. First, I'm just going to simply write out the alternate equation. I'm not going to modify it yet. I want everybody to see it and then see how it's modified. Since we're looking for a distance, I'm going to put the 2AD part on this side. Okay, this is the form of the alternate equation. Now we're going to modify it for what we have. So look, we get 2 times G, and I put the negative on there. Well, no, I'll tell you what. Let's just leave that off for right now. Let's just put our vector symbol on there, and then we'll put the negative in with the 9.8. H, we need to find H. That's our distance it travels from the ground up. And we know that it stops at the top. And we know we have an initial vertical velocity, v sub o y squared. So we're going to start with our initial vertical velocity. We're going to decelerate to a stop, and it'll tell us the distance h. So let's solve for h by dividing over by 2g, and this drops out because it's 0, and 0 squared is 0. So we get minus v sub oy squared over 2g. All right, now let's take a look at what we've got. We get negative 12.5 meters per second, and we're going to square the 12.5. The negative sign is not squared, remember? We're subtracting 2 squares. So this is not being squared, only the 12.5. Over 2 times negative 9.8 meters per second squared. Your minus signs tick out. There you go. All right. So if you plug that into your calculator, you should get that the height from the ground to the top, from where we had our initial velocity, vertical velocity, to the top, that height is going to be, 8 meters. But we want the distance from the roof to the top of the parabola. So the distance from the roof to the top of the parabola, I'm not sure what subscript to put on that, so let's just not put one on there. Okay, that's going to be h minus the roof height. I'll just write it out, that's easier. So that's going to be d equals 8 meters. The roof we said was 6.5 meters high. Okay. So the distance from the roof to the top of the parabola would have to be 1.5 meters. And that's above the roof. Boop, 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 boop. That wasn't so bad, was it? Nah, Okay. Now, On part B, they want us to determine the final velocity of the ball, magnitude and direction, because it's a vector. In order to do that, we need both components of the final velocity. At the moment, we only have one. So how do we find this component? Simple. We're going to use the definition of acceleration. Here it is. That's the definition of acceleration. Now let's modify it for what we have. And I'm going to also solve, well, let's solve for VF first, because that's what we want. So we get VF equals A times T plus V sub O. Now let's modify it. Okay, we want to find the final Y velocity when we accelerate for the time of the trip plus the initial Y velocity. So that's going to be negative 9.8 meters per second squared times 2.1 seconds plus 12.5 meters per second, because that was our initial. Oops, I didn't realize y'all couldn't see that. I'm sorry. That's going to be that's the initial vertical velocity that we already found. Okay? So now, when it strikes the roof, vertically, it will be traveling at, see if you get the same thing, negative 8 meters per second. All right? Why negative? Because isn't it headed down when it hits the roof? So we should see a negative come out on it. This is correct. All right, so now I'm going to bring that over here, negative 8 meters per second. Got it? Now we have both components. So we can say the final velocity is going to be the square root of 8.8 squared plus 8 squared. And if you stick that in there, you should get, I believe, about 12 meters per second. Somebody double check me. Oh, that's not the final answer. Hang on, I'm trying to box it in and it's not the final answer. Stop. There we go. Just underline. All right, so there's the magnitude. Now we need to get the direction. So we're going to take the inverse tangent of the tangent ratio. Since the horizontal leg is always adjacent to the angle, then we're going to put that on the bottom. Opposite over adjacent. So opposite is the vertical, adjacent's the horizontal. And if you stick that in your calculator, make sure you're in degrees, you should get about 42.5 degrees. So now our final velocity is 12 meters per second at 42.5 degrees above ground. Whoops. Okay, there you go. Sorry. Alrighty. In fact, if you want to see the triangle, I can draw it right over here so you can see about that ratio if you're not sure. So here, no, that should be above the roof, not the ground. It hit the roof. I'm sorry. I'm going to put roof right here, guys. Above roof. Okay. So when it comes down and strikes the roof, it has a final velocity at some angle, and that is made up of a horizontal component that we said is 8.8 meters per second, and this vertical component, which we said is negative 8 meters per second. And here's the angle next to the horizontal. We always measure from the horizontal, so there it is. Okay? So you can see 8 over 8.8, opposite over adjacent. Okay? And don't worry about the negative. Leave those out. When you're using Pythagorean theorem and your trig functions, just use the magnitudes. Don't worry about direction signs. Okay? And that's it. Tomorrow we're going to work on practicing some of these problems and see what we can do with them. Okay? All right. Talk to you later. Bye.